So today we're doing this. So as always, I'll encourage you, if you think you remember anything about doing this, pause the video and try one. The things to ask yourself would be, do I remember what either of these numbers are called? Because these things have names. Or do I remember how to do this? And if you remember how to do this, do it and see if you could come up with an answer. If you're drawing a complete blank, just listen in. So these numbers both have names. Okay, the most forgotten name is usually this one. This is called a base. That's not a name people usually remember as much. People tend more to remember this name, sometimes because it has two synonym options. Okay, this can be called a power, or this can be called an exponent. And those are used interchangeably. If I were going to read this problem to you, I would say that this is 3 to the 5th power, or more simply, maybe 3 to the 5th. Okay? 3 to the 5th power, or 3 to the 5th, what it means is we want to multiply a whole bunch of times. Okay? You probably remember from your earlier experiences in life or this year, multiplying was created to be a quick way to add. Instead of 37 plus 37 plus 37 plus 37 plus 37, they'd write 37 times 5. What this means, 3 to the 5th, is 3 times 3 times 3 times 3 times 3. We're going to multiply together a whole bunch of 3s. One common misconception sometimes with people is that you want 5 more 3s in addition to the base being 3. You want 5 total 3s. Okay, so we already see a 3. When we write our multiplication out, we only need 4 more 3s to total 5. So the power of the exponent is the total amount of the base that we want to see. So 3 is the base, lots of 3s, 5 of them, because the power does that count for us. And then we just multiply. 3 times 3 is 9. 9 times 3 is 27. 27 times 3, some people start to maybe get out of their range. So if you're out of your range on 27 times 3, you have two choices. One choice would be grab your pencil and paper and do out 27 times 3, and you turn out an 81 at that point. Then when you need to do 81 times 3, continue on with your pencil and paper and do it out. 243 is our goal. That would be one way to do that. 3 times 3 is 9, we're comfortable. 9 times 3 is 27, we're comfortable. When you get uncomfortable, start doing the rest of the multiplications on paper. Another choice would have been 3 times 3 was 9, 9 times 3 is 27, we got to here, we were comfortable with 27. Jot that down. If 27 times 3 made you uncomfortable, forget about that and continue to multiply other numbers. 3 times 3, we were comfortable. That's 9. Do that little group. Okay, so this group, we were comfortable with 27. This group, we were comfortable with 9. Now go pencil paper once, 27 times 9. Maybe that's better because you only had one pencil paper problem to do. Whereas these, you had to go pencil and paper like twice. Still get 243. No matter what order you multiply in, you'll get the same answer. These two powers have special names. So what I would suggest, if you remember anything about this, pause the video, see if you can retrieve those names. This could be read as 4 to the 3rd power, could be read as 4 to the 3rd, or there's a magic word for that. This could be 5 to the 2nd power, or just 5 to the 2nd, or we could say 5 and then have a special word for that. So if you want to pause. I'll do this word first. The little 2's we've seen this year, we saw them in yesterday's video actually. The 2nd power, those little 2's, we've talked about things being squared. We've done square inches and square centimeters. Instead of writing like SQ centimeters, we've done centimeters with a little 2. So that's not a shocking bit of news. The little 2's mean squared. So if I say 5 to the 2nd, I could also say 5 squared. 3 is the word cube. And I don't think we've done volume yet this year. When we do volume, there's also cubic inches to measure volumes of shapes, but we've not done that. But 3rd power is cube. But if I want to do this out, 4 cubed, you'd go 4 times 4 times 4. Lots of 4's because 4 was the base. 3 of them because 3 was the power. 4 times 4 is 16. 16 times 4, maybe you're comfortable with that, maybe you aren't. We're out of our times tables, so maybe we do 16 times 4 out, or maybe you can still do that in your mind. We're hoping to get 64 on that. 5 squared, we're going 5 times 5. We only need 2 of those numbers. Squared means there's 2 of the base, so 5 times 5, 25. If you think you got a hang of that, try to pause it, take on this column. This one will get a little bit big. This one's going to get a little bit big. So if you don't want those to get a little bit big while you're paused, maybe don't take those on, or maybe see if you can figure out a way to shrink them down based on some tricks that I'll do in a second. If you're back now, 2 to the 5th means we're going to go 2 times 2 times 2 times 2 times 2. There'd be 5 2's there. Again, the base just gets repeated a bunch of times. The power tells you how many of them. A common thing people do wrong on this is they'll end up multiplying 2 times 5 and only getting 10. That's not at all what we want to do. Exponent problems get big fast. 2 times 2 is 4. Times 2 again would be 8. 8 times 2 again is 16. 16 times 2 is where we're out of our times tables. So maybe you need to do 16 times 2, pencil, paper, do it out. But that's going to get us a 32. If we go to do 2 to the 10th, 3, 4, 5, 6, 7, 8, 9, 10 2's. Okay, you could go through the whole process and just go times 2 every time. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. That's as far as we got a second ago. We knew that that was 32. 32 times 2 is 64, but you might need pencil and paper to do that. 64 times 2 is 128, but you might need pencil and paper to do that. 128 times 2 is 256, but you might need pencil and paper to do that. 256 times 2 again is 512, but you might need pencil and paper to do that. And 512 times 2 would be 1024, and again, you might need pencil and paper to do that. I made reference there to needing pencil and paper like 6 times. Okay? You might not want to group it that way. Here's what I would have done if this were my homework paper I'm doing. If I just did 2 to the 5th, 1, 2, 3, 4, 5 of them makes a 32. These other 5 have to make another 32. And if I do 32 times 32, we'll need pencil and paper for that. But 32 times 32 is probably most people's quickest path to the 1024. 10 to the 2nd, we just go 10 times 10 for 10 squared, and that would get us 100. If we go 10 cubed, 10 times 10 times 10, the 10 times 10 originally was 100, throw on another 10, we'd be up to 1,000. 10 to the 12th, I'm not going to write out 12 tens. I refuse to do that. What I'm going to do is look here for a pattern. 10 to the 2nd ended up with 2 zeros. 10 to the 3rd ended up with 3 zeros. So it sort of stands to reason 10 to the 12th is going to end up with 12 zeros. Not 12 more zeros, 12 total zeros. 10 to the 2nd had 2 total zeros. 10 to the 3rd, 3. 10 to the 12th would have 12, and commas are definitely our friend on something that gets that big. Anytime the base is 10, the power is just going to tell you how many zeros there are. If you feel like you saw that before, you did on about the second week, third week of school maybe, we had a paper that had million, billion, trillion, quadrillion, quintillion, all the way up to like Google was on that paper. There were things like vigintillions and decillions and tridecillions is crazy. All these place value numbers up to 100 zeros. This is the way they wrote those, if you remember that paper at all. If you don't, that's fine. But the way they were writing those is with powers of 10 instead of, they weren't writing out numbers like this. They were writing out numbers like this. So when they were talking about a Google, 10 to the 100th was called a Google. Not Google like your search engine, but Google like the guy's name who wanted that to have that name. but that would be 100 total zeros. Lots of commas and such. Something to think through if you didn't yet. If you do 0 as the base and you take it to any power, there's something that will happen. It's an easier trick than the tens trick. Okay, when the 10 is the base, what happens is you get a certain amount of zeros based on the power again. If 0 is the base, what will always happen is you'll always just get 0. 0 times 0 times 0, you could do that all day long, it's just going to be 0. Likewise, 1 to any power has a trick. Okay, if we sit there and do 1 times 1 times 1 times 1 times 1 times 1 times 1 all day long, you do 1 as the base with lots and lots of powers, it'll always turn out to be 1. That's just a rule. If we get fractions, you do the same thing, you just have lots of fractions. So 3/5 to the 4th would be 3/5 times 3/5 times 3/5 times 3/5, and you just have to multiply straight across. 3 times 3 is 9, 9 times 3 is 27, 27 times 3, you might need pencil and paper. That'll get you an 81. Or if you don't like pencil and paper, 3 times 3 is a 9. The other 3 times 3 is a 9. A 9 times a 9 is still an 81. 5 times 5 is 25. This other 5 times 5 is another 25. Quickest way to do this might be to take 25 times 25. Or if you want to go, 5 times 5 is 25, times 5 again to be 125. Times 5 again, you're going to get up to 625, no matter what you do with that. Decimals, same kind of thing, just remember something about decimals. Fractions, remember to go straight across. Decimals, remember you have to count. Okay, so 0.3 times 0.3, just do 3 times 3 is 9. Like the decimals were never there, but then we're going to have to count. We'll count everything on the right of decimals. So to the right of this decimal, that 3 counts. To the right of this decimal, that 3 counts. We need to get a count of 2. To have a count of 2, we need a 0 to even have 2, and then the decimal goes in the beginning. Homework off of this, we're going to work from page 215, and we're just going to do all of page 215. Page 215 has letters that do the exponents, and then there's a 1 to 25 mix of all sorts of old and new things.